Today we're going to talk about 11.1, which is an introduction to sequences and series. A sequence is a list of values in any order whatsoever. And we have two kinds of those lists. They are either finite or infinite. Finite means there are an ending amount of terms involved. For example, the sequence 3, 6, 9, 12 has 4 total terms in it. Where an infinite sequence, 3, 6, 9, 12, and so on, and so on, and so on, does not stop. We cannot count to the end. Some information that you're going to want to know about sequences is what the notation for a term is versus the notation for what position it is in. A term is referred to as a sub n, and the actual term is 3, or 6 is a term, or 9 is a term, or 12 is a term. What position it holds would be considered n. The first position, the second position, the third position, and the fourth position. So if I want a sub 3, that means the term in the third position, which would be 9. So this is the term, and this is the position. The position is always referred to as the domain of the sequence. The term is the range. So if I'm looking at that finite sequence, the domain would be x equals 1, 2, 3, or 4. The range would be y equals 3, 6, 9, or 12. Notice that I listed each element of the domain. And the reason I do that is because there is no 1.5 position, 3.5 position, 2 3/4 position. The only positions that there are 1, 2, 3, 4. So the domain will always be the set of counting numbers, the natural numbers. Whereas a series is a sum of a sequence. And we use sigma notation. This will be new. That's a capital sigma in the Greek alphabet, and it always means to sum. So the difference between a sequence and a series is that a series will have plus signs in them. So here's our finite series. It's exactly the same as this one up here, only these all had commas. Now a series has pluses. So 3 plus 6 plus 9 plus 12. Or infinitely, 3 plus 6 plus 9 plus 12, etc., etc., etc. Now that's how you expand a series when you write it out. If we want to use our sigma notation, this is what we do. Notice I have my sigma, and then I have n equals 1 to 4. All that is my position, my counter. I have 1, 2, 3, 4 terms. So that is my position from 1 to 4 terms. Then, on this side of sigma is my general rule, which we will discuss in a little bit here as to how to generate those rules. But when it says my general rule is 3n, it says the first time put a 1 in there. 3 times 1 is 3, and that is my first term. Then a 2. 3 times 2 is the 6. That is my second term. 3 times 3 is 9. That is my third term. And finally, 3 times the 4 is 12, which is my fourth term. So the rule will generate the terms, and this tells me how many terms to generate from 1 to 4 terms. Likewise, we've done the same thing with the infinite series, but now I'm counting from 1 to infinity. I have 1 to infinitely many terms, still 3n. So when I put in a 1, I get 3. When I put in my 2, I get 6. My 3, I get 9. My 4, I get 12, etc., etc., etc. Alright, let's just try to see if we can expand and list some sequences. First of all, the rule says 5 minus n, and I'm to find the first 6. So I'm a blank person. I need 1, 2, 3, 4, 5, 6 of them. And since it's a list, they'll all be separated by a comma. Now realize, what I put in the blanks is my sequence. I'm just doing this for myself to keep track of it. So I'm going to change colors because my actual sequence will be in red. So the first time I'm going to put 1 in there. 5 minus 1 is 4. Then 5 minus 2 is 3. 5 minus 3 is 2. 5 minus 4 is 1. 5 minus 5 is 0. 5 minus 6 is negative 1. So in red, I have just generated the first 6 terms of this particular sequence. Let's try just one more. Again, I'm going to put my blanks to keep track of. I need 1, 2, 3, 4, 5, 6 of them. So 5 to the first is 5. 5 squared, 25. 5 cubed, 125. 5 to the fourth, 625. 5 to the fifth, 3,125. And 5 to the sixth, 15,625. Okay, now let's look at some ways to generate sequences. Sequences are all about patterns. When we want to find the repetitive pattern so that we can see a mathematical relationship from term to term to term will tell us what to do explicitly as a rule. Eventually, these patterns are going to be called recursive rules. And this thing that's called just a rule is going to be an explicit rule. Right now it's just referred to as a general rule. But I'm just going to let you know about that notation. So, if we look at the handout, we see first we have 3 in the picture, then we have 6, then we have 9. So let's start taking a look at this. From 3 to 6, what happened? Added 3. From 6 to 9, you added 3. So what would you expect to do from 9 to the next one? Add 3. So that would give me 12. 12 plus 3 would give me 15. So the pattern is to add 3 to the previous term. Now when you were back in grade school and you repetitively added 3, 3 popsicle sticks, 3 popsicle sticks, 3 popsicle sticks, 3 popsicle sticks. Did you learn to count 1, 2, 3, 4, 5, 6, 7, or did you eventually learn to take 3 times 4? Okay? So when you repetitively add, it means to multiply. So if I'm repetitively adding, it would mean 3n. So remember, your position is n and your term is a sub n. So if I put a 1 in there, 3 times 1, is that 3? Yeah, well let's check the next one. 3 times 2, is that 6? 3 times 3, is that 9? It's working. So this is the explicit rule. Why we call it explicit? Because it can get me to an explicit position. I don't need to keep on going, plus 3, plus 3, plus 3, to find the 10th term. I can just plug a 10 in here. 3 times 10 would be 30. 3 times 25 would be 75. So I can get to an explicit place by just using the rule. Where when I use the pattern, I need every term before it in order to move on. Okay, let's try another one. What's happening here? From 4 to 7, add 3. From 7 to 10, add 3. So what would you expect to do next? Add 3. So 10 plus 3 is 13. Add 3. 13 plus 3 is 16. So again, I am adding 3 to the previous term. And when I repetitively add, it means to multiply. So I'm at 3n. Now, let's put in a 1. 3 times 1 is 3. I'm adding, so what do I have to add to 3 to get to 4? 1. Let's see if it works. Substitute in a 2. 3 times 2 is 6 plus 1 is 7. Did it give me my second term? Let's try it for a fifth. 3 times 5 is 15 plus 1 is 16. Did it work? So I know that this is my rule. So what would the 10th term be? 3 times 10 is 30 plus 1 is 31. 3 times 25 is 75 plus 1 is 76. Are you understanding repetitive adding? Okay, let's look at a couple other examples. This time, what is happening from term to term to term? Add 3, add 5, so now what would you expect? Add 7, add 9. So from term to term to term, I am adding the next odd to the previous term. When I add odds, what's occurring? First time I have 1. Second time I have 4. Third time I have 9. Do you recognize any relationship there? N squared. 1 squared 1. 2 squared 4. 3 squared 9. 5 squared 25. Is it working? So what would 10 squared be? 100. 25 squared. 625. So anytime I repetitively add odds, I should get a square of some sorts. Let's try this one. From 9 to 16 is add 7. 16 to 25 is add 9. So add 11. 36. Add 13. 49. So it's still adding the next odd to the previous term. So I know it's going to be a square, some square. Well, is 1 squared 9? No, but what squared is 9? 3. So what do you got to do with the 1 to get to 3? Add 2. Let's see if that works. 1 plus 2 is 3. 3 squared 9. 2 plus 2 is 4. 4 squared is it 16? 4 plus 2 is 6. Squared is it 36? So it is working. So 10 would be 10 plus 2 is 12. 12 squared, 144. 25 plus 2 is 27. 27 squared, 729. So anytime you repetitively add odds, you're going to have a square. Okay, let's investigate a new pattern. This time what's happening from term to term to term? Multiply by 2, multiply by 2. So I am multiplying previous term by 2. So what happens when you repetitively multiply? Multiply by 2, multiply by 2, multiply by 2, multiply by 2. That's right, it would be multiply by 2 to the 4th. It becomes a power. So my ratio is 2. My power is what I'm looking for. Let's see. Is 2 to the 1st 3? No. But this time I have to multiply. So I can only multiply by that 3. I can't add to it. Now if I put my 1 in here, I have 3 times 2, which is 6. 6 is my second term. I need to go back a term. So what happens when you go back in mathematics? You subtract 1. Let's see if that works. 1 minus 1 is 0. 2 to the 0 is 1 times 3 is 3. 2 times minus 1 is 1. 2 to the 1st is 2 times 3 is 6. Is it working? 3. 2 squared is 4 times 3 is 12. So times 2 times 2. How are you going to do 100? Or excuse me, 10. It's going to be 3 times 2 to the 10 minus 1, which would be 3 times 2 to the 9th, which 1536. And this one would be 3 times 2 to the 25th minus 1. So that's 3 times 2 to the 24th. 5,033,000. Oh, 50 million. 331. 648. Okay, let's try another one. Divide by 2. When I divide by 2, that's the same as multiplying by 1/2. Multiply by 1/2. So 6 times a half would be 3. 3 times a half would be 3 halves. So I'm repetitively multiplying by 1/2 the previous term. So if I repetitively multiply, I know it has to be a power to the n minus 1 times my first term, 24. Anytime I have repetitive multiplying, I'm going to have a power of n minus 1. And then I need to multiply that by the first term. That's how I got back there. Let's just go back a second. Repetitive multiplying means I need powers of n minus 1. Repetitive adding meant to multiply by my difference. Repetitively adding odds meant to square whatever I was doing. 3 patterns to know. Let's try to graph it. It says to graph this above sequence. So I have 1, 3, 2, 6, 3, 12, 4, 24. What's this looking like? An exponential curve. Imagine that. The rule had an exponent. So when I graph repetitive multiplying and it involves exponents, I better get an exponential curve. But notice that I just have the points. I don't have them connected because we do not have a 0 term. We do not have a 2.5 term. So all I can have is a scattering of the points. Let's try this sequence. First I have 3, second I have 6, third I have 9, fourth I have 12, fifth I have 15. So these are my x's and these are my y's. 1, 3, 2, 6, 3, 9, 4, 12, 5, 15. What's this look like? A line. Because, remember this equation we generated was 3n. What is an equation of y equals 3x versus 3n? Linear. So when I repetitively add, I better get linear representations. One more special sequence to tell you about, and that is the Fibonacci sequence. Fibonacci sequence is this very sequence. 1, 1, 2, 3, 5, 8, etc., etc., etc. So can you recognize the pattern? Look at these two to see how you get to here. 1 plus 1 gives me 2. How do I get the 3? 1 plus 2 gives me 3. 2 plus 3 gets me 5. 3 plus 5 gets me 8. So what's the next one going to be? 5 plus 8 is 13. 3 plus 13, or 8 plus 13 is 21. 13 plus 21 is 34. So my pattern is to add the previous two terms. Then you have a Fibonacci. Let's see if we can apply this to a series. How do I know this is a series and not a sequence? Because I have plus signs. So summation notation means use your capital sigma. So I'm going to do my sigma. And then I'm going to look. What am I doing from term to term to term? Add 4. Add 4. So that means my rule is 4n. Let's see. When I put my 1 in here, do I get 4? Yes. 2, do I get 8? Yes. 3, do I get 12? Yes. Well, how many terms are there from 4 to 100? Well, I know I start at 1. And where do I end? Well, if we take our rule, 4n equals 100, won't I have n, my final n? So if I divide by 4, n is 25. So I go from 1 to 25 terms. And this thing is my sequence. N equals 1 to 25 of 4n. Let's try the next one. My sigma from 1 to infinity. Now let's see if we can find from term to term to term. From 2 to 3/4, we'll be subtracting 1 and 1/4. Is subtracting 1 and 1/4 get you 4 ninths? No. From 2 to 3/4, so it'll be 3/4 divided by 2 is times 0.375. 0.75 times 0.375 does not get me 4 ninths either. So it doesn't look like there's one rule that's repetitively adding or repetitively multiplying. But how about if we break it up into numerators and denominators? In my numerator, from 2 to 3, add 1. 3 to 4, add 1. 4 to 5, add 1. So I'm repetitively adding 1, so that's 1n. When I put 1 in there, do I get 2? No, I get 1, so I have to add 1 to get to the 2. What are you doing from 1 to 4? Adding 3, adding 5, adding 6, or excuse me, adding 7. So in the denominator, I'm adding odds. So then I know it must be a square. 1 squared 1. 2 squared 2. Yes. So here is my series summation. Now it's asking us to write the series and then find the sum. Add them all up. I'm starting with the 5th one and going to the 10th one. So I need the 5th, the 6th, the 7th, the 8th, the 9th, and the 10th. And I'm going to add all these up. So when I put my 5 in there, 5 squared, 25 plus 1, 26. 6 squared, 36 plus 1, 37. 7 squared, 49 plus 1, 50. 8 squared, 64 plus 1, 65. 9 squared, 81 plus 1, 82. 10 squared, 100 plus 1, 101. Now, just add all those up. 26 plus 37 plus 50 plus 65 plus 82 plus 101 gives me 361 for a total sum. See how to expand the series and then sum it. Just a few more things. We have some special formulas that we can use. Let's see if I can get this fixed up a little bit. Okay, sometimes it's easier to understand this way. This is saying I'm adding up a bunch of 1s. So let's say I'm going to do 4 1s. 1 plus 1 plus 1 plus 1 will give me 4. So my sum is automatically the same as my upper limit. The sum of 4 1s would be 4. If I went from 1 to 20, the sum of 20 1s would be 20. So all it's saying is whenever you add up 1s, it's going to be equivalent to your upper limit. Okay? Now this one is saying when I add up a bunch of first time 1, then 2, then 3, then 4, then 5. We'll stop there. Let's see what we get for a sum. 3 plus 3 is 6, plus 4 is 10, plus 5 is 15. Okay? Let's see what the formula says. It says n, which in this case I added up 5 of them. So 5 times 1 more than 5 is 6 over 2. Does that still give me 15? 30 divided 2 is 15. So if you know the formula, it's a quick way to get to the sum without having to add them all up. Because if I had 1 to 1,000 to add up, it'd be a lot faster to do this than it would be to write all 1,000 out and add them up. And the last special formula is I squared. So the first time 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Let's just do 5 of them again. So here I have 5 and 25 is 30 and 25 is 55. Okay? Well, let's see what the formula says. It says take how many you had, 5, add 1 more to it, 6, 2 times how many I had, so 2 times 5 is 10, plus 1 is 11, and then divide by 6. So these would reduce, and I'd have 55. I still get there. Okay, so let's find the sum of these using our special formulas. I want to show you something you can do. I could say this is the same as 4 times the sum of 1 to 15 of n. So if I take 4 times all of this, it's the same as 4n, correct? Well, n, 1 to 15. So it means 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So it's this formula right here, isn't it? So it's 15 times 16 over 2. But I still have this 4. So let's reduce here. So 32 times 15. 480. It's a quick way to get to the sum. Rather than have to add up 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11 plus 12 plus 13 plus 14 plus 15. Add all that up and then multiply by 4. We can do it this way. Let's go to the next one. This time, we're adding a bunch of 3's. Is that the same as saying 3 times the sum of 1 to 115 of a bunch of 1's? How many 1's do you have here? 115 of them times 3 should give me 345. There's a lot to practice there. Let's give it a shot. Do your best. We'll look through it tomorrow.